job introducing, so I'm going to continue to do that. Oh, also, one other quick thing, my daughter insisted I bring back some of the local currency from Athens, so if anybody can find any, I'll appreciate it. We're very happy to, oh, I didn't ask you your title, but it's here. Yeah, okay. We're very happy to have Nick Stelter from University of Chicago. He'll talk about surface bundles over surfaces with multiple fiberings.
Thanks to Dan, thanks to Will, thanks to all the other organizers. It's been a real pleasure canoeing and hearing all of these great math talks. So I'm going to talk today about surface bundles. So let me start by reminding you what these are. So a surface bundle is what you probably would guess it would be. It's a fiber bundle with fibrous surface over some base space B. So at this point, I should get my sort of conventions and stipulations out of the way. I'm usually going to take the fiber to be closed, and I want to take G to be bigger than or equal to 2, because most of what I'm going to be talking about is kind of how you study these and what the relationship to the mapping class group is. And so when G equals 1, there's kind of a whole separate theory to this. The other stipulation that I want to make is that, of course, you can study fiber bundles over whatever kind of base space you want, but I want to take B to be a closed, probably oriented smooth manifold. So we're kind of approaching the realm of geometry as opposed to just topology. The other term that I should introduce at this point is that of the monodromy. So the monodromy is a map that's attached to a surface bundle, and without sort of writing down a formal definition, which would take all day, it's a homomorphism from the fundamental group of the base space into the mapping class group of the fiber. And what this does is if you have a loop in the base, you kind of look at how the picture of what your fiber is changes as you traverse this loop here. And this will be one of the central pieces of data that will be important in what comes next here. So what I want to start by talking about is kind of what the ultimate inspiration for this project was, even though ultimately this doesn't end up sort of playing an actual role in the mathematics that will follow. And this is the story of the Thurston norm. So we've already heard kind of somewhat of a parallel theory from Spencer and from Chris about how a similar sort of story might work for automorphisms of free groups or, let's say, free bicyclic extensions. The original context for the Thurston norm is for 3 manifolds. And so the idea of the Thurston norm is that it's a semi-norm on H2 of a 3 manifold with real coefficients. And you can get rid of the semi-assumption if the manifold is, say, hyperbolic. And Thurston showed a lot of amazing properties of this thing. So first of all, what is this measure? So if I have some class X in H2, the Thurston norm, which I'll write maybe norm sub T, this measures, in some loose sense, the minimal complexity of an embedded surface sigma that represents the homology class. One of the most important features of the Thurston norm is that it's not just some sort of arbitrary norm that you put on this vector space here. It has this very rich combinatorial structure. And in fact, what Thurston showed is that it's a finite-sided rational polyhedron, by which I mean the norm ball. So let's call this B sub t the set of x in H2 such that x t is 1 is a finite-sided rational polyhedron. So the picture that you want to keep in your head is something of the following. So suppose I have second Betty number equal to 2, so I have this two-dimensional space. Your Thurston norm ball will end up looking something like this. It has to be symmetric about the map x goes to minus x because it's a norm, and up to the symmetry constraint. One of the things that Thurston showed is that there are basically no other constraints in what these rational polyhedra can look like. but this is a kind of basic example. So one thing that you can do with this, once you have this structure of a finite-sided rational polyhedron, is you can start studying cones on faces. So by this I just mean the R plus span of the classes that live on a particular face. And you end up carving out your second homology into all of these sort of finitely many different pieces, each of which is sort of determined by finitely many linear equations. And where this story starts to connect up with the math that I want to talk about is Thurston investigated what happens when the manifold that you're starting with has the structure of a surface bundle. In this case, it's a surface bundle over the circle. And in this case, the fiber of this particular surface bundle structure is a class in H2. And so it interacts with this whole picture. And it lives somewhere in this vector space as an integral class. And so Thurston's question was basically, well, where does it live? And he showed the following. So let's say that sigma G M S1 is a surface bundle. Let's let class of sigma G denote the fiber. And so Thurston showed two things. The first is that he showed that this class here, sigma G, lives in the interior of a cone on a face here. So this is a valid picture for a fiber. A class that lives on the boundary of one of these cones will never be the fiber of a fibration. So it lives in the interior of a cone on a face. The second thing that he showed is that, in fact, let's say the following, that if C is such a cone, that is, it contains some class of a fibering. And this is the really amazing thing. If C is such a cone, then every other integral class in that cone is also the fiber of a fibration. So every other x in C intersect the z points of your homology, I guess modding out by torsion, but you have this lattice of integral classes inside here. So every other, let me just emphasize that, every other class here is also the fiber of a fibration. So let's write it something like sigma h to e, sorry, m, not e, to s1. So I've indicated here that the genus is going to be different. In fact, you can detect what the genus is of the fibering by evaluating it on the Thurston norm. Implicit in this is that sort of fibers are minimal complexity. But it turns out that the value of the Thurston norm on a class tells you the genus of the fibering. Also, in the setting where you have a genuine norm, so for example, if you start with a pseudo-Anasov element of the mapping class, then another theorem of Thurston tells you that your manifold will be hyperbolic, and so this semi-norm here will in fact be a norm. And in this case here, what you can see is that necessarily there's only finitely many classes whose norm is bounded by whatever constant you want. So in fact, you can find fiberings of the original manifold with arbitrarily large genus. Although again, in the case where you have a genuine norm, there's only finitely many fiberings of every given genus. So this is kind of the basic picture of surface bundles over the circle. And one of the essential features of them is that it's common for them to have infinitely many fiberings. I should point out that the one situation where this doesn't happen is when your first Benny number is equal to 1. In this case, you only have a unique fibering, and this is because you just simply don't have any more room to accept kind of a cone with an interior and other classes. And this will be important for what I want to talk about next, so let me just record this fact, that M3, if you start with the fibering, so if I have a fibered 3 manifold, so M3 fibered fibers in infinitely many ways if and only if B2 of M, or B1, I guess, if we're closed, is bigger than one string. Okay, so this is kind of the basic inspiration for the work that I want to talk about. And I want to talk about how much of this same story can be told for surface bundles over surfaces now. So instead of 3 manifolds, we're thinking about 4 manifolds. And the first remark is that this might sound kind of naive or crazy. And the reason for this is that if you know kind of how the theory of the Thurston norm works, it's really not a theory about surface bundles per se, it's a theory about manifolds that fiber over the circle. And fiberings over the circle interact really nicely with a lot of kind of the topological structure. To find fiberings, you find closed one forms, etc. And fibering over a surface, finding these is a much sort of more meaty process. It's not as, I mean, I don't want to say simple, but it's much more complicated to sort of find fiberings over surfaces. So you might think that it would be sort of a crazy project to sort of try and study surface bundles over surfaces with multiple fiberings, just sort of taking as your sort of basic inspiration or toolkit the Thurston norm, because a lot of this just simply doesn't transport to higher dimensions. And there are significant differences between the theory of surface bundles over surfaces and that of over the circle. So I want to touch a little bit on sort of the new stuff. But I also want to tell you about one thing I was able to show, which is a direct parallel of one of the facts that we've already talked about, although it ends up going by completely different methods. So I think it's kind of interesting, both from a mathematical and a philosophical point of view, that the same theorem should be true. So let me tell you about that theorem first. So now my setting is I have a surface bundle over a surface. So this is now a 4 manifold. G and H are both at least 2. These are closed surfaces. And so attached to this, I have my monodromy representation. So this goes from pi 1 of the base space, sigma H, into the mapping class group of the fiber. And the assumption that I have on this is something about the cohomology. So let me put this down here. So the assumption is that the following twisted cohomology group vanishes. And then I'll explain why this isn't such a crazy piece of nonsense as it might seem. So what I want to consider here is H1 of sigma G. I guess you could probably take rational coefficients, and you take the invariant cohomology. So let me remind you what this is. So by definition, the invariant cohomology of sigma G, twisted by the action of rho, is the following. So what I do is I just take H1 of sigma G, and now I have the action of the monodromy. That is, it tells me what happens. As I move around the loop in the base, how am I acting on my fiber? How am I sort of changing the surface by transporting it around the loop? And so I can look at this kind of on the level of up to diffeos up to isotopy, which then allows me to get actions on other sort of topological invariants I can attach to this, like the cohomology. So what's happening here is I have this action of transporting the fiber around the loop, and I ask, how does this change my cohomology? So the invariant cohomology here is I take the cohomology of the fiber, and then I identify classes if I get one from the other by transporting around the loop. So this is H1, and then maybe I'll write my mod this way. So I identify all V that are equal to rho x of V for x in pi 1 of the base. And so
coinvariance, not the invariance.
Oh, yeah, no, sorry. The assumption I want is on the invariant, but yes, no, you're right. This is in fact the coinvariance. Coinvariance and invariance sort of have a dual theory to them. But no, actually, thank you for pointing this out here. So this is just, yes, I guess we didn't need to go down that road after all. But, okay, I mean, no big loss. So this is just the set of the in H1 sigma g such that V is fixed by all rows. So it's just globally invariant under the actions. Yes, thank you. Okay. For all sigma. I want sigma h. Yes, okay, great. You could also ask for the covariance, but we don't actually need to do this. So what am I assuming about this? Suppose that this vanishes. That is, there is no globally invariant cohomology classes. Under this assumption, this four-manifold has a unique surface bundle over a surface structure. So this is the conclusion of the theorem. Then let's call this projection map P here. So then e to sigma h is the unique, and I guess I should say up to fiber-wise diffeo, because you're never going to have completely unique bundle structures because you can always post-compose with some map that changes the base around or something. So up to fiber-wise diffeo surface bundle structure.
So it's not up to bundle isomorphism?
So by bundle isomorphism, do you mean covering the identity?
Exactly. Yeah.
Well, no, because that, I mean, you can destroy that by just sort of post-composing with some automorphism of the base. So fiber-wise diffeo is what I really want here. And in fact, something even stronger is true, where I impose some conditions about the fundamental group. But for the purposes of this talk here, fiber-wise diffeo is fine. So why does this fit within the picture?
Equivalence?
I'm sorry?
That's a weaker equivalence?
Fiber-wise diffeo?
Yeah.
Weaker versus stronger. It's possible to have two things that are fiber-wise diffeo that are not bundle isomorphic, because bundle isomorphism requires that you have this map on the total space, and you get a map on the base space that covers the identity. And that's too strong for our purposes. So why does this fit in with the whole picture of the Thurston norm? Well, it comes down to this fact here, that what does it mean to have second Betty number equal to 1, which is the situation in which you have a unique fibering? Well, if you compute so I guess you can compute the first cohomology of a fibered 3-manifold. So maybe I build this as the mapping torus of some element phi here. And I guess with Q coefficients, this is exactly the same thing as, so I pull back the cohomology of the base, and I'll just slightly abuse notation here. So this is H1, S1. And then the other part of your cohomology is exactly the invariant cohomology here. So H1 sigma g, if this is acting on the surface of sigma g, that's phi invariant. So the assumption that the first Betty number or the second Betty number is equal to 1 for a fibered 3-manifold is exactly to say that this piece vanishes here. So this theorem is a direct counterpart to one direction of this fact about fibered 3-manifolds for the case of a surface bundle over a surface. But as I said before, the method of proof is completely different here. I mean, the method of proof in this case is essentially, I mean, it's not very deep. You just realize that when you have one dimension of cohomology, every class is a multiple of a primitive class. And that will mean that, you know, you kind of have only one fibering up to sort of taking parallel copies of your fiber. In this case here, you actually have to do some work. And this boils down to some facts about surface groups, which maybe I'll get into later here. But I want to point out that, so the first thing that you might think is like, oh, okay, well, if it's true for base of dimension 1 and true for base of dimension 2, then maybe it's sort of a general fact. But there doesn't seem to be any sort of obvious way to take this and bootstrap it up to higher dimensions. Yes?
Well, you raised something I was going to ask earlier. So in the 3-manifold case, if you just compose with a double cover of this circle over itself, are you considering that a different vibration? Or?
Well, so I want connected fibers.
Connected fibers, okay. Yeah. So same thing in the 4-manifold, you could just compose with a covering of the base
Yeah.
of some other surface. That's
Yeah.
not right.
But no, connected fiber, I guess, should be an assumption. I guess it's implicit
Maybe
in
you
writing
said
sigma
that,
G, but
right, yeah, sorry, I didn't see
yeah,
that.
no, it was very, very tacit in what I said.
Well, okay, so in the Thurston, you know, the Thurston result, every other integral class, do you mean primitive integral class then?
Yes,
Every other
thank
x,
you.
that number 2 there.
Yeah, that's a good point. Okay. So on the one hand here, I'm not going to talk much more about this theorem here, but I do want to point out that it is possible to repeat some of the story that comes out of the Thurston norm for surface bundles over surfaces, although not necessarily kind of in full generality. So I would be interested to know if this is a general fact, that if you have just any surface bundle over some k-dimensional manifold, if this condition on the vanishing of the invariant cohomology gives you a unique surface bundle structure. So let's sort of switch gears a little bit and talk about kind of where this theory of surface bundles over surfaces parts ways with the Thurston norm. So the very first thing that you might ask is how many different fiberings can you get? I mean, the sort of punchline, or one of the punchlines of the theory of the Thurston norm, is that the answer is often infinity for a surface bundle over the circle. And so the very first fact about multiply fibered surface bundles over surfaces is that this is never going to happen. So this is a theorem due to not Dennis Johnson, who will make an appearance later, but F.E.A. Johnson, I'm just going to use the notation SBS for surface bundle over surface, so we're not here all day watching me write out surface bundle over surface. So any surface bundle over a surface, by which I mean implicit in this that G and H should both be equal or bigger than 2. So any surface bundle over surface has only finitely many fiberings. Again, up to fiberwise diffie, and again up to something slightly stronger than fiberwise diffie. So the way you prove this is, again, it rests on kind of special facts about surface groups that I guess probably in the interest of time is not worth sort of unpacking too much, but just to give you a sense of kind of how this follows. So this raises kind of one big major question, which I'll pose as a problem. So the problem is how many? So to make this slightly more mathematical, let's introduce a function which I'll call n of gh, and this is going to be the maximal number of fiberings of some 4 manifold, which you can realize as a surface bundle with fiber G over base space H. So this function, I take all surface bundles with fiber G and base sigma H, and I just ask how many fiberings can I get here. So my proposal here is to study this function ngh. In Johnson's proof here, there's implicit in this a very, very weak bound that depends both on G and H. It essentially, so it depends on kind of the product of the Euler characteristics, and then you ask for how many index D subgroups, or index at most D subgroups, are inside pi 1 of sigma H, where D here is the product of the Euler characteristics. So that's a terrible bound. And I want to get it better. So question 1.
Should those lower bound or upper bound?
So there are at most K fiberings, where K is the number of index D subgroups of pi 1 sigma H, where D is the product of the Euler characteristics.
So that does imply that it's actually finite.
Yes.
Yeah. Well, the theorem says if you fix a particular SBS, that there are infinitely many with MGH, depending on how you.
Oh, yes. I see your point. Yes, that's a good point. Sorry, so the observation here is that this function here, it could be that, you know, for a fixed G and H, I could build bundles with, you know, arbitrarily many fiberings. But the point here is that this is, in fact, a finite number. Thank you. So, right. So, first question is, okay, can I find anything at all with two fiberings? I haven't told you about surface bundles over surfaces with multiple fiberings. So, can this be bigger than one? And the answer is yes, for kind of stupid reasons. Take sigma g times sigma h, and this has two fiberings. So I was a little bit dismissive of this at first, but it actually turns out that you can build very, very interesting examples of doubly fibered surface bundles over surfaces, and the mechanism by which they pick up two fiberings is that these things are closely related. That is, they admit some sort of low complexity map to this, which then gives you your two fiberings by post-composing with these two fiberings here. So what I want to do next is discuss my favorite example of a surface bundle over a surface in some detail here. And let me just sort of anticipatorily make some more space. Oh, we're running way behind schedule. So this example is due to Atiyah and Kodaira independently. And so here's how the construction goes. What I'll do is I'll start with the surface, and the smallest one for which I can do this is a surface of genus 3. Because what I want to have is I want to have a free involution of my surface, which I might call tau. Now, I'll consider the product bundle sigma 3 times sigma 3. So horizontal here is the base direction, and then these vertical surfaces are the fibers. And what I'll do is I'll, in effect, take a multi-section of this bundle, if you like. But just to unpack that, what this means is at each point in the base, this corresponds to a whole surface sitting over it, and I just want to pick out some collection of, in this case, two different points sitting over the fiber. So I have the diagonal section of this product bundle where, so let's call this point Z1 here, and this maybe corresponds to this point. And here's Z2, and this corresponds to this point here, and then Z3 is up here. And then having this free involution allows me to pick out a second point that's always going to be different. So if this is Z1, I'll also pick out tau of Z1, tau of Z2, tau of Z3, etc. So I have this product bundle where I've picked out two special points that are varying as I move around in the base. And I have these 2 points here. So what am I going to do with this? The idea is to take this collection of data, these 2 points in the fiber, and take a double branch covering, where the branch points occur at the points where I've picked these out. Now there's an obstruction to doing this. You can't always just willy-nilly say, okay, I'm going to take all of these fiber-wise, or this fiber-wise branch covering. But this obstruction sort of has to deal with, or has to do with kind of the divisibility of this codimension 2 submanifold in cohomology. To be precise, so you consider the element in H2 that corresponds to this sort of union of two surfaces that you pick out. And I want to make this divisible by 2 in homology. And it's not, so the way you solve this is you take a particular covering of the base space, and when you pull it back there, you end up getting something that's divisible by 2. So without saying too much more about this, you take some covering, and this is now going to be a surface of genus 129. This is the Z mod 2 homology cover of sigma 3. And you still have fibers of genus 3. And what you can do is now sort of the obstruction to taking this fiber-wise branch covering vanishes, and so you end up getting this 4-manifold E, which is constructed by, in each of these fibers, I take the double branch covering over the particular points that I've specified here. So I get E4 by modding out by some action of Z mod 2. And so this is the construction that I want to have here. There's maybe another cartoon that's worth drawing at this point, just to give you another sort of take on this. So here's our sigma 3, here's our other sigma 3, and then here's just a kind of representative cartoon of what the sort of diagonal and tau times diagonal section look like. And then I can sort of cover this by sigma 129, and I get kind of a few more copies of the diagonal section, and then I cover this. And you can sort of see why this manifold has the first property that I want to talk about, which is that it has two fiberings. So the first fibering, I should point out here, well, okay, let's talk about it. So I have this map E4 to sigma 129 times sigma 3. And if I then project onto sigma 129, in effect what I'm doing is I'm just recording the fact that I took this fiber-wise branch covering here. And so this manifold E has a surface bundle structure over a base of genus 129. And what's the genus of the fiber? Well, I took a double branch covering. You apply Riemann-Hurwitz, you see that the genus is 6. So one structure is sigma 6, E sigma 129. And that's sort of projecting onto this direction. But I can also project onto the other direction here, because this is just a trivial bundle. And in this case, so I project onto sigma 3, and you can again apply Riemann-Hurwitz, or you can just do an Euler characteristic computation. And what you see is that E has the second fibering over a base of sigma 3 with genus 321 fiber. And so I want to point out here that if you're studying doubly fibered surface bundles over surfaces, this is a pretty typical thing to happen. It's not that you have, 3 different fiberings, all, genus 7 over genus 2. You have just totally different ways of mapping to surfaces of different genus with fibers of different genus. They all sort of get packaged together, usually by a construction something like this.
So are you expecting us to see right away why that map to sigma 3 is a fiber?
So you can use something like Ehresmann's criterion to just see that it satisfies like a differential topology criterion for fibering. But I mean, essentially, right, if you just use Ehresmann's criteria, you just need to check that it's this proper surjective submersion. And you might have some sort of problem with the places where you ramify. But because you're sort of ramifying diagonally.
That's diagonal, I see.
Yeah.
That's surjective. Yeah, okay.
Yeah.
Okay.
So in the interest of time, I'll maybe just sort of mention a few of the other properties that this manifold has. So Atiyah and Kodaira, when they constructed this, were not trying to construct a double fibered surface bundle over a surface. The problem that they were trying to solve was to construct a surface bundle over a surface with non-zero signature. Signature, of course, being the quintessential invariant of the 4 manifold. And so one thing that you can do is you can compute what the signature of this 4 manifold is, and you can see that it's non-zero. In fact, it turns out to be 256. And I should give a hat tip to Dan Margulies, who told me a very nice way of computing this using vertical vector fields. So the observation that this bundle is doubly fibered originally came from symplectic geometry. So this is an observation of Claude Lebrun. And what Lebrun was interested in is the problem of symplectic manifolds that admit inequivalent symplectic forms. So this story really ultimately goes back to Thurston, who showed that surface bundles over surfaces, where the genus of the base and the fiber are at least 2, that all surface bundles over surfaces are symplectic manifolds. The way you construct your symplectic form is you sort of patch together the area form on the fiber and the area form on the base, and this gives you a symplectic form. And the interesting thing about this is that the symplectic form, and it's not a canonical thing, you get sort of an array of them, but these symplectic forms that you construct, they're built out of the fibering data that you get. And so what Lebrun realized is that this example here has two different fiberings. And so there's two different methods for building symplectic structures. And he used this to show that the two different classes of symplectic structures are inequivalent in the sense that one cannot be deformed to the other through symplectic forms. And this was a question that people in symplectic topology were interested in, is this even possible? This was the second example.
Are they symplectomorphic though? Or is that known?
I don't actually know. So Lebrun showed that the two symplectic structures are inequivalent. Okay. So one sort of thing that I want to drive home here is that this example here does a lot of different things for you, and it has a lot of remarkable properties kind of coming from different areas of mathematics. Great. So we've now seen an answer, what I hope is a fairly satisfying answer to the question of whether this maximal number of fiberings is at least 2. I mean, it's a yes, kind of for immediate reasons, and it's also yes in slightly more interesting ways. But so here's another question you can ask about the number of fiberings function. So we've seen bundles with 2 fiberings. Are there bundles with 3 fiberings? So I can phrase this as follows. Is the number of fibering functions identically equal to 2? This is an open question. Nobody knows the construction of a surface bundle over a surface with at least 3 inequivalent fiberings. And so what I want to talk about next is some work that I've done to give a partial answer to this question. It's really not kind of the end of the line, but let me tell you what it is that I can show. So the theorem is that we have a surface bundle over a surface. And I'm going to put a fairly strong constraint on the monodromy representation, but so be it. So the monodromy representation, sigma h to mod sigma g, the constraint that I want to put is the following. Suppose that the image of rho is contained in this subgroup of the mapping class group written kg. This is known as the Johnson kernel. So what is this? Kg is just those mapping classes that are generated by Dane twist T sub gamma, where gamma is a separating simple closed curve. And so under the assumption that your monodromy is built out of compositions of separating twists, I can show that any such bundle has at most 2 fiberings. So then E has at most 2 fiberings. And I can do even better than that. In the situation where you have exactly 2 fiberings, the only way this can happen is if the bundle itself is a product of surfaces. So if you have a surface bundle over a surface with monodromy in the Johnson kernel, unless it's trivial, it has a unique fiber. And if E has 2 fiberings, E is diffeomorphic to sigma g times sigma h. Okay. So the basic sort of problem in attacking something like this is how to detect the existence of other fiberings. You start with a sort of very inhomogeneous picture of your four-manifold, where you build it by taking a surface and sort of gluing in a family of surfaces over it. So how do you get a handle on where other such ways of constructing the same four-manifold might come from? In the case of a surface bundle over a circle, there's this very nice organizing principle, the Thurston norm. And you sort of transport the problem of studying fiberings onto the problem of studying certain types of closed one forms. And there's this very nice sort of package that kind of tells you where all of these fibers live. But in this case, there's just not an organizing principle that sort of allows you to sort of instantly pinpoint where the different fiberings might live. So you have to get kind of a little bit, you have to get your hands dirty. And so the principle that underlies how this work is done is to go by the cohomology ring and detect fiberings by sort of detecting how different pieces of the cohomology ring of the total space interact with each other. So the principle is to study H star of E. You can even do this integrally. In fact, in some parts of this, you have to kind of run simple divisibility arguments that you really need integral for. So, I mean, this is great, but how do you compute something like this, or what is kind of the principle that we're going to be using? So let me tell you the basic fact that underlies how you sort of use the cohomology ring to study fiberings. And this is a very general fact about fiber bundles. I've seen this attributed originally to Burrell. So fact, theorem. So suppose I have some fiber bundle of closed-oriented manifolds, so not just surface bundles, and not just surface bundles over surfaces. So suppose I have this, and the assumption that I want is that the Euler characteristic of the fiber is not equal to 0. So we have the projection map P, and the theorem is that then the pullback of the cohomology of the base space injects into H star E. So for our purposes, we can apply this as follows. So I mean, the assumption that G and H are bigger than 2 tells us that this theorem applies. And so what we do now is every time you have a fibering, you have an injective map from the cohomology ring of a surface into the cohomology of your total space. And the thing to realize is that the cohomology ring of a surface has some nice special algebraic properties that sort of follow from the fact that it has this symplectic structure in the degree 1 piece by, just sort of intersections of curves. The algebraic intersection number is in symplectic form. And this puts sort of strong constraints on where it can end up living inside the total space here. And this is the basic principle that drives what happens. But this is only really as good as your ability to compute the cohomology ring of the total space of a surface bundle over a surface. And that's really kind of the heart of what goes into the theorem that I wrote down here. And really, this theorem here is just kind of an application of the computation that I did of the cohomology ring of a surface bundle over a surface. And you can do other things with them. I should point out that one of the major things you can do with this is kind of get a new perspective on something like the Johnson invariants from the theory of the Torelli group. You can sort of re-understand these as, from this point of view, sort of about the cohomology ring of surface bundles with Torelli monotomy. That's maybe more for the experts. So let me write the following problem. Compute the cohomology of sigma G, sigma H. So the way I computed this is I transferred the problem to computing the homology with intersection pair. So if you have a closed manifold, you have this sort of dual theory of cup product, where if you have embedded closed manifolds that represent homology classes, if you put them in general position, you can intersect them, and you get a new closed manifold, and the codimensions add, and this is a sort of geometrization of cup product. And so the approach that I took here was to, instead of studying cup product, study intersection product. And instead of building cohomology classes, build homology classes, build embedded manifolds representing homology classes that you can then intersect and sort of read off information from in a very combinatorial way. So let me just sort of show you what this looks like, because really it all boils down to just sort of drawing some nice pictures. So I have to use the word spectral sequence at this point, unfortunately. Don't worry, I'm just going to write this on the board and then forget about it. So a spectral sequence computation, which Morita did, is that it tells you kind of additively what the cohomology of this looks like. I mean, for the experts, you know, it's feasible to read off sort of additive structure, but computing ring structures in cohomology from spectral sequences is in general, I guess, if not entirely impossible, then much, much harder. But you can get the additive structure of a surface bundle over a surface this way. Essentially, he just shows that it degenerates at the E2 page. So sort of cohomologically, it's a product, or I guess I should say homologically, it's a product. So you see that H star E is non-canonically a direct sum. H star E, or...
This is assuming Torelli monodromy?
So actually, in general, it's not assuming Torelli monodromy, but you have to have twisted coefficients. So maybe I should just write this as follows without sort of... let me extract the piece that I want to show for you. What I want to show for you in the remaining 10 minutes is a little bit of what this looks like in the case of a surface bundle over a surface. I'll just describe for you H upper 1 and how to compute the cup product structure. So dually, I want to tell you about H lower 3. So I'm going to be building 3 manifolds inside 4 manifolds for the remainder of this talk here. So let me specialize to this case here. And in this case, I can do this with twisted coefficients, but let's just specialize to the Torelli monodromy case, where you don't have to worry about that. So H3 of E is, again, non-canonically a direct sum of 2 pieces. So the first piece, this might look a little bizarre, this P upper shriek here is the image of H1 of the base under the Giesen homomorphism. And I'll show you exactly what this means on the level of sort of manifolds in a second. So if you don't remember what the Giesen homomorphism, don't worry, I'll tell you. And then I direct sum onto this. I take H1 of the fiber, and the invariants show up again. So the invariant under the monodromy, and this is what this looks like here. So let's draw some pictures. So the first picture is what does this sort of P upper shriek piece look like? Well, so here's my base space sigma H, and let me get the colors. Here's some class X. So sitting over this, I have some fibers, and all I do in sort of computing this Giesen homomorphism is I just take the induced bundle over some, representative submanifold for this. So the Giesen homomorphism of this, one way of building 3 manifolds inside this type of 4 manifold, is just to take the induced bundle over this loop here. So I sort of have a circle's worth of surfaces. And from the point of view of computing something like cup product or intersection product, this is very, very doable. All you need to do is sort of understand if I have an X and I have a Y, or maybe it's something like this, I have another induced bundle. The only places where they intersect cover places in the base where they intersect. Each time I intersect in the base, I end up picking up a copy of the fiber. And so the intersection product of classes of these form is completely determined by the cup product structure on the base. So the more interesting part of this happens in the second piece here, the invariants. And so what's the idea here? So I just want to sort of draw you a picture of how you compute these. And give you an indication of how you can then sort of read off the cup product structure from these. So my starting bit of data is I'll take some class V in each one of the fiber that's rho and varied. And let me sort of blow up the base at this point. So I guess this is sigma H. So implicit in this picture here is I'm sort of taking some sort of cell structure on the base here. This I only have these 2 1 cells, so maybe this is over a torus, but for the purpose of visual simplicity, let's just work here. So what I've drawn here, here's the 0 cell, these 2 lines are 1 cells, and then the rest of the blackboard is a 2 cell on a cell structure for a torus. And I have a bundle over it, so I have fibers sitting over each of these points here. And actually this example requires 5 holes. So I have this, and let's take the following curve, where I just sort of wrap around this side, and then I wrap around on the back. So we'll call this gamma here. So what the action of the monodromy does is I have 2 mapping classes alpha and beta, and every time I cross over one of these cells here, the action of the monodromy changes my picture by some element of the mapping class group. And so the example that I'm doing here, let me just sort of compress this picture a little bit and only draw the front of the surface. So maybe it takes gamma and then it just sort of wraps this around the other direction. The thing to realize here is that what I've just drawn here is compatible with this condition that V is an invariant class here. Because if I look at the union of gamma, which I guess represents V, I didn't say this, so gamma and alpha of gamma together co-bound this genus 1 surface here. And so this is exactly what it means for the homology class V to be invariant, is to say that whatever representative I have, it doesn't need to be fixed on the level of homotopy, but it does need to be fixed on the level of homology. So that is to say that if I take the curve and its image under the monodromy, they end up co-bounding a surface. So this will come back into play in a second here. Let me just sort of show you what I had in mind for the other couple of directions here. So, I need a hole. So let's have beta act on gamma by wrapping it around 2 here. So again, this now co-bounds the surface of genus 2 boundary components. And if I do alpha and beta, let's say that it ends up wrapping around all the way here. So what I'm going to do is I'm going to take this class in the fiber, and from it I'm going to build a 3 manifold. And so the one that I want to take is on the interior of this 2 cell. I just take this curve crossed with the interior of the 2 cell. But what the picture looks like changes as I move around in the manifold. So while this is topologically just a D2 cross an S1, sort of you have to glue it up compatibly, and that's where all of the magic happens. So let's now think about how to glue this up with this. And what I see is exactly what I sort of hinted at before, that you co-bound some surface here. So on this 1 cell, I'm just going to take this picture and cross it with the 1 cell. So as I cross over from here to here, I can sort of interpolate between these 2 different curves by gluing in this manifold which sort of caps them off. And then I just sort of take this in each of these pieces here. And there's kind of a problem, which is that on some neighborhood of where all of these 1 cells come together, I'm doing different things. And so what you do is you realize that, in fact, as you go all the way around here, you're describing something that's null homologous in sort of this little bit here. And so then, for abstract reasons of just kind of differential topology, you can glue in some mystery cap here that sort of finishes off the problem and gives you this embedded submanifold. And you know exactly what it looks like kind of everywhere except in this mystery region. And now the good news is, if you want to compute intersections, you don't need to know what it looks like in this piece here. So let's think about how to intersect 2 of these. And what you do is you sort of put things in general position by taking a slightly different cell structure. And if I had some other curve here, well, let's think about sort of over this point here. No, maybe that's not what I want to do. Let me just sort of say the following here and wrap things up here. So what I want to say is that the cup product structure here, the intersection structure, is exactly computable in terms of the Johnson homomorphism and the higher Johnson invariance. So for those of you who are unfamiliar with this, let me just sort of tell you what the Johnson homomorphism is algebraically. It's this map tau from the Torelli group, and you can sort of make the target be a couple of different things, but for our purposes, we can take this to be wedge 3 of H1 of the surface here. And one way of describing this is sort of, this is recording the cup product structure in a mapping torus with Torelli monodromy by taking 3 classes that you build sort of in this way by sort of taking 2 curves and interpolating them. And then you can ask about triple intersections of these. And so to sort of make a slightly long story short, this turns out to be a homomorphism. It's well studied, and it's sort of one of the central features of the theory of the Torelli group. And what you see here is the exact sorts of constructions that you do to build the Johnson homomorphism end up sort of getting crossed with an interval as you sort of glue these bundles together. And the sorts of intersections that you see happening end up sort of being completely describable in terms of what the Johnson homomorphism is. And so I'm pretty much out of time here, and I didn't get a chance to talk about how you actually take this construction and use it to solve the problem or prove the theorem that I wrote down here, but I guess you'll just have to ask me about that after the talk. There's a few steps. So the first step is to realize that the assumption of the image of rho being contained in Kg, that this implies that on the level of cohomology, not just additively, but multiplicatively, H star E is a product. So what the Kunda formula would give you is that this is H star sigma G, tensor product, I guess the non-squeaky with H star sigma H, where this is a tensor product of rings, so you can compute the cup product structure just sort of algebraically. I should point out that this is not totally trivial here. It's trivial, or not trivial, but sort of immediate from the fact that the cup product structure is read off from the Johnson homomorphism that sort of the products in H1 will vanish, but implicit in this is sort of a computation of the restriction of the second Johnson invariant to Kg, and I show that that vanishes. And so at this point, you just kind of transfer your problem to an essentially algebraic one of proving that a product of 2 surfaces has at most 2 fiberings. But only you're allowed to use the cohomology ring, because I've just showed that these things have the same cohomology ring. And so what you do is you sort of look at the pullback of a second base, and you ask, where does H1 of mystery base live? And using sort of the structure of the multiplication here, and the fact that there's a lot of pairs of classes that multiply to 0, that interacts very poorly with the way that this ring structure actually is. It's hard to have pairs of elements multiply to 0. And in fact, it's so hard that H1V has to be contained inside H1 of this or H1 of this. It can't sort of sit diagonally inside them. And that really is kind of the crux of the argument. Yeah, I mean, since this is after the talk and I'm answering a question, I won't sort of dwell on this, but the essential piece of this is to realize that once you have this sort of cohomological product, any other base has to be contained in one piece or another here. And that's kind of the lever that you use to then do the rest of the problem. Yeah?
So you can compute, I guess, cup products in these mapping for using the first Johnson homomorphism basically. Well, smart stuff. So in surface bundles over circles, you can compute Massey products using higher Johnson homomorphisms.
Yes.
Is there a parallel story here?
I mean, there should be. I think it boils down to constructing the right examples.
Because you can do those intersections. I mean, those are like sort of triple intersections and things like that. So they're sort of
Yeah. I mean, I can tell you, I haven't thought about this for surface bundles over surfaces, but I have thought about how to compute Massey products using higher Johnson homomorphisms. I mean, I think essentially the same sorts of constructions should work. Just kind of this cut and paste stuff. But I haven't had occasion to do that. But yes, I guess in principle, Massey products here should be computed from higher Johnson homomorphisms.
Other questions?
Yeah.
Are there any known examples, or non-trivial examples, with Torelli monodromy where there's more than one?
So that's a great question. I thought there wasn't, and I went so far as putting a conjecture that, you know, this story for the Johnson kernel should extend to Torelli. At lunch yesterday, Dan told me an example that I haven't sat down and thought about it, but it may actually be possible to build surface bundles over surfaces with Torelli and non-Johnson kernel necessarily monodromy that have two fiberings. So stay tuned.